All right, welcome back. So next up is I want to talk about errors on the analysis side, errors of model building, errors that you might be committing as we are looking at stuff. So I've mentioned this concept to a few of you in various discussions as we're going through the project, right? So there's a part of the project where what we're doing is we're asking, hey, is algorithm A statistically significantly better than algorithm B? Over these data sets, is it definitely doing a better performance level than B? The problem is that statistics are an excellent way to hide the truth if you use them wrong. There is the difference between something being statistically significant and it being relevant in any kind of practical way. What do I mean? Imagine that somebody is selling a drug to cure baldness. Okay? And they get a lot of investment interest because they publish a paper showing that their treatment produced hair growth in a statistically significant way. Well, if that statistically significant hair growth is about, peach fuzz deep and just kind of barely there, that is not practically relevant. It's not relevant, that hair growth, until it gets to the point where you have to go to the barber to get your top, get this top and sides trimmed back. Okay? So this is the problem. There can be all kinds of things that are statistically different in condition A and B that we don't actually care about. And making sure when you're doing any kind of comparison among predictions that your systems are making, that you successfully distinguish that the effect of your whole system, whatever it is one which is not just statistically significant, but relevant, is quite important. So at this point, I can't recall if I've brought up Anscombes Quartet in this class already or not. What it is it's 4 data sets that have been used as examples through the years. As you can see these 4 data sets here in the subgraphs, what you can also note on the right-hand side is that these 4 data sets have exactly the same descriptive statistics. They have the same mean, the same variance, the same correlation between X and Y, and importantly, from the standpoint of machine learning, if you fit a regression line through them, you get the same slope and intercept. And yet these are radically different data sets. Why is this the case, that we have all these same measures? Well, it's because 3 of the 4 violate an important assumption of normal statistics in linear regression, right? These are not, things which are actually linear. They're not, they're not homoscedastic. They're heteroscedastic. They have increasing variance in the lower left there. They're not evenly distributed across the x-axis, right? There's all kinds of problems. So this is kind of like a life lesson. The idea is that if you don't understand an algorithm's assumptions, you probably can't recognize when data violates it. So here you are using fancy machine learning technique that comes out in 2 years' time that I don't even know a name for, right? And if you don't know what this algorithm assumes about the data, then you can't know that the data you're working with are violating the assumptions, and the answers you're getting out of this are bogus. So this is my plea that everybody should please understand theoretical bases as much as they can, instead of just using a software library because it's the new buzzword. Okay, so another thing is it matters how you structure your model, okay? If we just assume that what we're doing here is we're fitting a linear regression and that's that, you can get a different result if you break things up into subgroups. So this is a thing called Simpsons Paradox, and it stems from a famous case where UC Berkeley was sued for sex discrimination because admissions to the graduate school looked super male heavy and, may have been anti-feminist. But the problem is this, right? In this particular case, that wasn't true once you broke it up for subgroup analysis. Now, I want to be super clear. I am not saying here that there's not a sex discrimination problem in general, because there is a sex discrimination problem in general. The thing is that in this particular case in 1973, it turned out not to be true. Okay, so with the whole setup here, if you had broken up and looked at the admissions of women on the top there and men here, you could see the ones that got in blue. Oh, my head is covering the... Right. So in blue, you can see the accepteds, and in red, you see the rejected people. Okay, so it looks like here that the proportion of women, 30-ish% that got accepted versus 46% of men got accepted, it looks like there's a discrimination. Okay, but if we break this up into subgroups in the different departments, there's actually a small bias in favor of women. How does that work out? Well, we've split up that group of women and men into their departments of application, right? And what you can see is that in some cases, the proportion in each department looks very much the same, right? These are cases where there's pretty much the same number of female applicants, sorry, not the same number, the same proportion, the same percentage of female applicants getting allowed in. Okay, and in Department A, actually, there are very few women applying, but almost all of them are getting in. So I believe that Department A is like physics or math or something like that in this. Okay, so what does this look like? Well, if you fit a line of regression across the whole group, then it's a negative correlation between, gender and admission. All right? But if you fit according to the subgroups, right, then there is a positive correlation running the other way. Okay, so this is Simpson's Paradox. This is the idea that if you do the analysis at one level, you get an answer. But if you do it at a different level, pulling out subgroups, you get a very, very different answer. So this is a lesson for model builders, right? Oh, this is not the one I wanted. That's the one I wanted, right? This is a lesson for model builders. You should know that the form of your model matters. The assumptions you're making matter. So even if you're not making a statistical model like this, which has explicit setups, but rather some machine learning predictor, it still matters what you're doing with the data and how you're structuring the algorithm to succeed. So another error of analysis is that when you don't try to structure the algorithm, you just say, hey, algorithm, solve this for me, right? You don't have any control over how the algorithm solves the problem. It's a black box. You're controlling for your outputs, but you're not controlling for how the whole thing is generated. So highly under-constrained algorithms, like deep learning networks, they can solve problems in a variety of ways. And they can end up solving the problem in ways that you don't want it to, fundamentally, right? So it turns out that when you ask this kind of neural network to learn to caption images, then it learns associations like a green hillside must be grazing sheep. And even if you feed it a green hillside that has no sheep in it, it will produce an image label of sheep. okay? Because it learned some weird structure in the data there. If you give a, label this object kind of neural network a pattern of random noise like that gray square there, it's going to hallucinate a teapot because there's some pattern there that when it initiates activity in the neural network produces teapot. Obviously, we don't perceive it that way, but the structure of visual recognition for this algorithm is quite different than the structure of visual recognition for a human being. The scan there, this chest x-ray one, is a setup where they were trying to recognize pneumonia. Okay? And it was, trained on a variety of data, including, x-ray machines at hospital A, B, and C. And so it was quite good on hospitals A, B, and C. That was no problem. But when they tried to use this prediction on a brand new hospital, machine D on a different hospital, it was terrible. Why was that? Well, what it turned out it was doing is it was using elements that are, this is the attention of the neural network, this red stuff. There's a little token here, which indicates which X-ray machine took the image. So it was learning to recognize which machine was doing the scanning. And it turns out that in hospital A, there's quite a lot of pneumonia, and in hospital B, there's not that much, and in hospital C, it's a very low rate, right? And so it was learning to condition its response based on which hospital it was in, which was certainly not the intent of this algorithm. They wanted it to predict pneumonia given the patient. Look at the patient's X-ray, not which hospital it's in, right? And, this is a text processing program here, and it learns to produce right answers unless you give it distracting information. If you add on totally irrelevant information there in blue, then the sentence goes from the correct answer of John Elway to the distractor of Jeff Dean. Okay? Algorithms don't solve things the way we do, and that can lead to problems down the road for you, right? The metric that you've set up, that you're looking at right now, may look great, but put it into production or, just shake the system a little bit and suddenly it produces very different results. I forgot to turn myself back on. Okay. So let's talk a little bit about accountability. This is a brand new topic, actually, a completely different direction. So, I'm going to break here. I'll do a set of super short ones. So the idea here is that what we've covered so far is that we've looked at errors of the measurement side and errors of how you construct your neural networks and, or whatever it is that you're going to do machine learning wise, or do your statistical analysis, right? And those two things are a good solid foundation for at least starting to think about how this problem is going to arise in the rest of your machine learning career, okay? But the last part that I'm going to get into in the next one is about the ethical side of stuff. So I'll see you again in 1 minute. Ciao for now.